Welcome to this video on the quantum nose. We're discarding the classical biology of smell. The human nervous system acts as a microscopic quantum spectrometer, not just a detector of molecular shapes. The lock and key model fails to explain the isotope anomaly. Standard models assume olfaction is purely shape-based. However, isotopes have identical shapes but vastly different weights. This proves that shape alone is insufficient for sensing smell. Olfactory receptors read molecular vibrations, not just structural geometry. Luca Turin pioneered quantum vibration theory, proposing inelastic electron tunneling. Our receptors are biological spectrometers, detecting the quantum harmonic frequencies of specific molecular bonds. Step 1 is defining the potential well, mapping the quantum landscape of the G-protein coupled receptor. Think of the receptor as a physical landscape with two cliffs. The electron is trapped on the higher cliff, ED, and wants to reach the lower cliff, EA. The trapped electron cannot cross the energy void without shedding excess energy. The absolute energy gap is delta E equals ED, EA. The electron must shed exactly delta E to drop into the acceptor well, as classical elastic tunneling is impossible here. Step 2 is the harmonic oscillator. Odorant molecules are dynamic systems of quantized, vibrating springs. Atomic bonds act as quantum harmonic oscillators. When you inhale an odorant, you are inhaling a complex system of vibrating springs at specific, quantized frequencies omega. The specific vibrational frequency of the chemical bond is the scent. The vibrational energy of the molecule is mathematically locked to its frequency. E vibration equals h bar omega. Every molecular bond has an absolute quantum energy signature. Step 3 is wave function overlap. The trapped electron feels the odorant via an evanescent wave. Before the electron even jumps, its probability cloud extends into the binding pocket. When the odorant docks, it creates an electron-phonon coupling. The electron and the odorant become a single mathematically coupled system. We must calculate the system as a whole. Hat H equals hat H electron plus hat H vibration plus hat H interaction. The coupling, hat H interaction, represents the physical interaction between the tunneling electron and the odorant's vibration. Step 4 is the inelastic tunneling event. The electron jumps, violently kicking the molecule into an excited state. The molecule acts as a bridge, absorbing the exact amount of excess energy the electron needs to shed to complete the tunnel. Fermi's golden rule governs the absolute probability of the quantum jump. This equation dictates the rate of the tunneling event, acting as the ultimate gatekeeper for the quantum nose. Physical alignment and vibrational probability control the tunnel rate. The transition matrix element dictates how well the wave functions overlap. The Franck-Condon factor dictates the exact probability of the odorant successfully transitioning its vibrational state. The Dirac delta function enforces absolute quantum energy conservation. This is the ultimate biological filter. The function evaluates to 0 unless the energy gap exactly equals the vibrational energy of the odorant. No resonance equals no tunneling, and therefore no smell. Step 5 is biological transduction. The successful quantum jump acts as a physical trigger for the nervous system. The arrival of the electron alters the receptor's electrostatic landscape, uncoiling the protein, detaching the G-protein, and firing an action potential. Your brain is actively running an inelastic electron tunneling spectroscopy computation. You are not just smelling the shape of the molecule. Your nervous system is computing the subatomic quantum harmonic vibrations of chemical bonds, using Fermi's golden rule to process sensory data.